There's an alternative graphical analysis of electrostatics in MOSCAP. You get the same answers from equation as well as from here. These are also equations, but sometimes it can provide you with more insight. So what I'm going to do is quickly remind you a few things and address a few important issues. Right. So let me remind you about the energy band diagram. Right. So we have metal SiO2 p-type. We have said that the way we draw the energy band diagram, we take the system apart. Right. Each element is isolated. Metal SiO2 p-type. We draw the energy diagram of the isolated system. Right. So we're well familiar. Work function here, work function of the semiconductor, and then we bring them together. And then, of course, we know charge transfer occurs, Fermi energy equalizes, right? So we know this. Fermi energy equalizes, and we get a band diagram, which is shown over here, right? So you have, and as a result of, because the semiconductor and the metal Fermi energies initially are different, you get a built-in potential. And we have seen that we can calculate the built-in potential, which is this metal. In the way the diagram has been drawn, the metal is at a lower energy as compared to the semiconductor, which means that the metal is at a higher potential. So psi ms, psi m minus is equal to phi s minus phi m here. So there's a built-in potential, and what we have to do is to create flat band condition, then we have to apply a potential opposite to that. So built-in potential is phi sm. So we have to apply a potential opposite to that, and which is what we call as the flat band voltage, phi ms. And Q, of course, is there to convert energy into voltage. And this is a band diagram at equilibrium. If I draw a band diagram with a gate voltage, let's say VG applied, then again, by the same process that we had used earlier, we can show that VG minus phi ms by Q equal to the drop across the oxide plus the drop in the semiconductor. Right, so this is the fundamental equation that we had derived here, and this, of course, is under the assumption that we are not okay. So that's the equation that we had derived here. Right now, very quickly, a minor point which sometimes we miss here is if I look at this diagram here. If I look at this particular diagram here, I just said, and we all agreed that for the MOS system, VG minus phi ms by Q is the effective voltage, and that's equal to the drop in the oxide plus the drop in the semiconductor, right? So that's the fundamental equation. Let's forget this for a moment here, and let's look at this diagram. So the voltage between here and here is VG. Where is this voltage dropped? Across the oxide and the semiconductor. So why am I not writing VG equal to V oxide plus IS? There's a voltage VG applied between these two terminals. The voltage is dropped across the oxide, which is Vox. Yeah, but where is the flaw? The voltage I've applied between VG and ground, if you look at it, the voltage should be the drop across the SiO2, which is Vox, and the drop across the semiconductor, which is IS. Which contact potential? Right, so where am I missing? You're right, what I'm missing is, if I look at this picture, what I'm missing is VG equal to Vox, fine, plus the drop in the semiconductor, but then I've not reached the other end ground. And how do I reach the other end ground? From here to the ground here. So actually, this is referring to these drops, and I have this additional drop here. So when you see this phi ms, where is it coming from? Actually, I should have VG equal to Vox plus the drop in the semiconductor plus the drop across the contact here. And what is the drop across the contact? The drop across the contact node would be equal to the voltage in the semiconductor here minus the voltage of the metal here, psi s minus psi m. And this is equal to what? Phi ms by Q. So that's where this one is equal to the phi ms by Q here, right? So VG. So when I write VG minus phi ms by Q, what is it referring to? It's not referring to the total voltage drop from here to here. It's only referring to VG minus phi ms by Q is the voltage drop from here till the semiconductor, bulk of the semiconductor. So what we are saying is the effective drop from here till the bulk of the semiconductor is Vg minus phi ms by q, and that's equal to the drop here and the drop here. We're not referring to Vg and the ground here. If you refer to Vg and the ground here, then of course this is the. Alright, so let's come back to the graphical analysis. So what we've been saying is the following. So if we look at our MOS system, so we said we can, it's helpful if we sketch the field. We start from the field here. And so there are two parts to sketching the field. One is in SiO2, the other one is in semiconductor. And in semiconductor, we sketch the field when there's uniform doping. We remember the Poisson's equation, dE by dy is minus Q by ES Na here. And we know field inside the bulk is 0. So we start here. This is the depletion with W. And the slope is negative. So we sketch that out and we say this is the field in the semiconductor here. I'm talking about depletion right now. So this is the field in at the surface, at the interface, which is ES here. And we know we have done lots of depletion region analysis, and we can write down what is ES, let's say field at this point here, in terms of the surface potential. Potential with respect to bulk here, so psi S, 2q Na psi S by ES here. So that gives us the field here. So, so this is the field here. Then we remember that we apply Gauss's law here at this interface, and so this gives us the field in the oxide here, and the field in the oxide is higher as compared to field in the semiconductor here by the ratio of the permittivities here. So we get this field here. So we can sketch the field inside MOSCAP, and then we remember that Vg minus phi ms is the effective voltage. As I go from gate to the bulk here, the effective voltage is Vg minus phi ms, and that must be equal to the integral of the field here. So which is area under the this graph here. And once we take the area under the graph, then for example, the area under this part is nothing but psi s. If we want to write it in terms, we can write the area under the graph either in terms of ES or in terms of E oxide or in terms of psi s. It depends on what we are looking for. So if I want to write it in terms of the potential, surface potential here, then this area is nothing but surface potential here, psi s. ES we know in terms of surface potential is here, so we can write out E oxide. And the drop here is E oxide into T oxide, which all boils down to this equation. Okay, so we end up getting this equation which is valid in depletion. So you solve this equation for a given gate voltage, and you will get the surface potential. And once you get the surface potential, then of course you have depletion widths, and you have everything else that you're looking for here, right? And this equation can also be used for estimating the threshold voltage, because at threshold voltage we are saying that the charge, inversion charge, is just, the system is just entering into stronger inversion. And I'll show you later on in the discussion today, the amount of inversion charge at threshold is actually very small. The amount of inversion charge at threshold is very small. So practically you have the same situation as far as the fields are concerned. There is an inversion charge, but it hardly alters the value of the field here. Okay, so the same situation prevails at the threshold. Threshold is a boundary between the depletion and strong inversion. So almost the same situation prevails at threshold. So if you want to estimate the threshold voltage, all you have to do is, we've said threshold is a point where the electron density at the surface is the same as the hole density in the bulk, which corresponds to psi s equal to 2 phi f. So all we do is we just put 2 phi f here, and we put 2 phi f here, and we end up the gate voltage at which this occurs, we get the threshold voltage also. All right. So this analysis is an analysis which one has to do many times. Depletion, and as I said, if you put surface potential equal to 2 phi f, you get the threshold voltage also. When you go to inversion, strong inversion, then the picture changes, because in addition to this depletion charge, I have my inversion charge also. So the picture now, if I were to draw again, note that in the bulk, what do I have? Depletion charge. And inversion charge, we have said, is confined to the surface, and the width of the inversion charge is very, very small. Okay. So what we can do is, again, as far as the bulk is concerned, I'm going to have electric field in the bulk which goes like this here, according to this expression here. d by dy equal to minus qs by na, so it goes like this here. But then, as I approach close to the surface here, now in addition to this negative charge because of the dopant atoms, I have electrons also. And so what, and of course the field is here. and I have electrons also. Now electrons is also dE by dy is what? In addition to that, what will my Poisson equation become? D by dy equal to minus q by es Na minus q by es times the electron density. So Poisson's equation now will become this minus q by es, the electron density. And electron density is rising very sharply. So that's why now the field rises very sharply here. So although the field here, if it were only the depletion charge, the field will go to Es, but then the field rises very sharply because of the strong, and we are talking about strong inversion charge. So there is a large amount of inversion charge, so the field rises sharply here. But then this, it's not drawn to scale. This region is very, very small in width here. The inversion charge region is very small here. I can write ES1 as ES. Note ES is whatever is the field at this point, let's say, minus Q inversion by ES. How do I write this? The field at this point minus the field at this point should be equal to what? The difference of the two fields. Let's say this is the field here is ES here, and this is the field ES1. So the difference of the two fields, what does Poisson equation say? The difference of the two fields is charge. But actually in this small region, I not only have inversion charge, but I have a little bit of depletion charge also, which I'm neglecting because this region is very small. And we are saying strong inversion. Okay. So ES1 is ES minus Q inversion by ES here. Right. So this is the picture that we have here. Okay. So the field goes like this, and then very close to the surface, builds up very fast here, goes up high here. And then of course, we have the standard Poisson's, Gauss's law here, and this field will give us a field in the oxide. And then that's the picture, field picture in strong inversion. And again, we have Vg minus phi ms equal to the integral of the area under the graph here. Now, when we take area under the graph, what we do is, so there is this area E oxide into T oxide here, so that's fine. When we take area under the graph, we ignore the area under this one because it's very, very narrow. Okay, we've shown you whenever we have an N plus, and if you have a depletion region in N plus, it affects the field, but its contribution to the voltage is negligible. So when I go from here to here and I integrate this, the area under this particular part is negligible. Most of the area or the voltage comes from this particular part. So that's why when we write Vg minus phi ms, that's equal to, this is the, this area under this particular part is 2 phi f, which we assume that the surface potential remains constant at a value equal to 2 phi f. Not strictly true. Again, we'll discuss it a little bit later on in the course. 2 phi f here. So this is area under the graph. So the whole area under the semiconductor is the area under this part plus area under this, which we are neglecting. So that's basically equal to 2 phi f, right? And the field here, the field is made up of ES, which is here, and the inversion charge. So the field part, this E oxide into T oxide gives us this particular part. Okay. And so this equation that you see here, one can also then take this particular part, phi ms and all this, one can club it into, basically this is equal to threshold voltage. So we get Vg minus Vt equal to minus Q inversion by C oxide. So it says once you cross the threshold voltage, inversion charge changes linearly with the gate voltage minus the threshold voltage. Yes, which you have seen, which we had derived in the notes itself. But we have, looked at it from another angle, which is the through a plotting of the field and then integrating the field here. All right, so that's strong inversion. When we come to accumulation, as I said, to complete the story, accumulation. So what is the picture here in accumulation? The fields are going to become negative. So accumulation, let's again draw here, and dE by dy is Q by ESP here. Right, so now the only charge that is present is because of holes that you're accumulating, and this is positive. So positive means it's going to slopes are like this here, right? Why have I drawn a slope like this? And again, because it's accumulation charge here. So just like inversion charge, the accumulation charge is confined very, very close to the interface. It's very close to the interface here, and so the region where the accumulation layer exists is a very thin region. Accumulation layer is very thin here, so that's why it's drawn like this here, with a very sharp slope here and a very narrow region here. So that's ES here. And then, of course, and what is the value of ES here? ES minus 0 here, whatever is the field outside is 0. So ES is nothing but Q accumulation by ES. If I apply Gauss's law, the field here at the surface minus the field which is in the bulk, so the difference of the two fields is nothing but the charge which exists in this area. So that's the Q accumulation charge here. Okay, fine. So once we get this here, then of course same equation holds here. One can write down the field in the oxide here, right? And again we have to take the area under the graph, which will give us Vg minus phi ms here. Now when we take area under the graph, what do? What is the area under this? Area under this is, again, fields are very strong, but this is a very narrow region. So area under this is practically negligible, right? So compared to, for example, if you look at it, this region is what? T oxide. T oxide could be 10 nanometer, let's say 100 angstrom or so, and this region is very, very small, 1 nanometer or 2 nanometer, right? So it's very thin. So we ignore the drop here, and when we take it, then it becomes Vg minus phi ms equal to the drop here is Q accumulation by C oxide. And if you want to be accurate, you can say the drop here is nothing but the surface potential. But we are saying surface potential is what? Practically 0. Very close to 0 here. That's what we are saying. The drop here in this is close to 0 here. And therefore, we can write Vg minus phi ms is equal to Q accumulation by C oxide. So if you want to estimate how much is the accumulation charge, well, whatever is the gate voltage minus phi ms, and that gives you the accumulation charge by C oxide. Under the assumption that this drop here is negligible. Okay, so that's why the approximate sign is there. So that sort of completes. We have accumulation, we've seen depletion, and we have seen the strong inversion also by plotting the electric fields. All right, let's go forward and look at, say, I want to compute flatband voltage. All right. So suppose I have a system like this. If the system is free of any charges in the oxide, we have seen the flatband voltage is simply phi ms. But suppose I have a sheet of charge here inside the oxide. Sheet of charge is described by a delta function, and it is inside the oxide. And the value of this sheet of charge is QF. Right? Is QF. And I want to know how much is the flatband voltage now. Because note that earlier the difference in the work function was creating a band bending. Now this sheet of charge, if I have a positive charge here, what is this positive charge going to do? Positive charge will be mirrored by some negative charge, right? And so it will try to induce negative charge in the semiconductor. And charge in the semiconductor only comes through band bending, right? So it will create a band bending in the semiconductor also, which means that I have an additional, even though I may have applied no voltage, let's say 0 voltage, I have band bending due to this charge in the oxide also, in addition to the work function difference. So it's going to affect my flatband voltage. So the question that we are asking is, what is the new flatband voltage when we have a sheet of charge located at this particular interface, and the magnitude of the sheet of charge is positive? It's a delta function, and its value is QF. So now the issue is, how do we calculate that? Again, there are different routes of calculation. We can go ahead and sketch the field. We've been trying to solve all electrostatic problems associated with MOS capacitor by sketching the field. So one can sketch the field here. So we are saying we want to calculate flatband voltage. What is the meaning of flatband voltage? Is the voltage that I need to apply here to make the band flat, right? To make the bands flat inside the semiconductor. All right, so let's sketch the field here. I'm sketching the field at flatband voltage. So what is the field in my semiconductor? 0, everybody agrees, bands are flat. So I start by sketching 0 field. Okay, 0 field. Now, the moment I go, this is a delta, it's a sheet of charge. The moment I go into the oxide, what will happen because of this? Apply Gauss's law. What will happen to the field? Field here minus the field here is equal to, right? So what will be the field then? Immediately this is the field 0 here. So immediately next, I've not drawn a real delta function. You can see a bit here, but immediately next to it, into the oxide, what would be the field? What would be the value of the field? How much will be the field here? See, this is the equation, Poisson's equation, dE oxide by dy equal to now the charge, right? The charge is here times E oxide. Is that equation correct? Note that this charge is per centimeter square, and this gives you another 1 by centimeter. So the whole thing is charge per unit volume. Okay. So this whole thing is charge per unit volume divided by E oxide. So if I integrate it, what will I get? I will get a value of E oxide here, whose value will be equal to minus QF by E oxide. Is that correct? Note, we are going in this direction is equal to, sorry, I should correct this. Is that correct? Field here is negative. Right? Field is negative. And then once we integrate this area under the graph, what should we get? Vg is, normally we write Vg minus phi ms. What is Vg? V flat minus phi ms is equal to area under the graph. And what is the area under the graph now? Area under the graph is, is equal to QF minus QF by E oxide multiplied by T oxide. So there is T oxide. So now that's, so our threshold our flat band voltage then becomes equal to flat phi ms minus QF by C oxide. That's the flat band voltage. Does it make sense that if I have a positive charge here, I have to apply a negative? What he's saying is I have to apply a negative voltage. I have to apply a negative voltage to make the bands flat. Does it make sense? Because positive charge here, normally what was this positive charge doing? It was going to induce charge here, negative. But then when I apply negative voltage here, so this negative charge now compensates this positive charge. So that's why minus QF by, there's a negative term. So it makes sense here, right? Now suppose this positive sheet of charge that I put here, if it were located right at the metal, what would be the flat band voltage? Right? So it's not going to affect if it is at this end, it's not going to affect my flat band voltage, right? Why does it not affect? Equation tells you what happens then. Huh? Yeah, Tox is 0, fine, but what is really physically happening? So earlier this one was inducing charge here, right? Next to it, it was creating negative charge here and was causing a band bending. And we had to remove that band bending by applying a voltage here. When you take this particular charge and put it here, where does it induce charge? It induces in the metal itself. It doesn't do anything here. So it doesn't have any effect. Okay, fine. All right, so now you people have become expert at graphical analysis. So let's do this. I have a system, MOS system here. I have uniform doping Na, but in addition to a uniform doping, what I have is sort of a sheet of an additional high doping very close to the interface. And that high doping, I'm just modeling it as a delta function. So in addition to uniform doping Na, I have a doping which is N0 times delta X0. Again, I've put delta X. I think I should put everywhere delta Y because I'm plotting everything as a function of Y here. All right. Okay, so Na times Y here. Right. So the issue is I have a sheet of doping now. This doping. Okay, it's doping here, N0 delta Y, and of course Na is there throughout. Now what I want to do is calculate what is my threshold voltage. How much is my threshold voltage? So again, the idea is that you sketch the field. You sketch the field, and then you take area under the graph, and then you'll have the threshold